Welcome to Chapter 2 of the Intermediate Spintronics series. In this chapter, we'll study spin transfer torque, the mechanism by which spin-polarized current can switch magnetization. Independently predicted by Slinksiewski and Berger in 1996, SDT is the operating principle behind SDT-MRAM, which is now commercially available. We'll learn the theory, dynamics, and device applications. Spin transfer torque occurs when spin-polarized electrons flow through a magnetic material. In a magnetic tunnel junction with a fixed pinned layer and a switchable free layer, electrons become polarized by the pinned layer. When they enter the free layer, angular momentum conservation requires the lost electron's spin angular momentum to transfer to the magnetization. This creates a torque that can switch the free layer. The physical picture is straightforward. Electrons become spin-polarized as they pass through the pinned magnetic layer. They traverse the non-magnetic spacer while maintaining their polarization. Upon entering the free layer, electrons with spin components transverse to the local magnetization are absorbed, transferring their angular momentum. Slinksiewski and Berger independently predicted this effect in 1996. Slinksiewski formulated the spin transfer torque quantitatively. The torque is proportional to current I, spin polarization P, and inversely proportional to area A, saturation magnetization MS, and free layer thickness TF. The angular factor G of theta captures the spin-dependent transport physics. The double cross product M cross MP gives the torque direction perpendicular to both magnetization vectors. The Slinksiewski G-factor determines how SDT efficiency varies with the relative angle between free and pinned layer magnetizations. The G-factor is smallest when the magnetizations are parallel and largest when they are anti-parallel. Note, though, that the torque itself carries an extra sign of the angle, so it actually vanishes at both perfectly collinear states, and switching has to be nucleated by a small thermal tilt. This angular dependence has important implications for switching dynamics and stability. Magnetization dynamics is described by the Landau-Lifshitz-Gilbert equation extended with spin transfer torque. The equation has three terms: precession around the effective field, Gilbert damping that relaxes magnetization toward equilibrium, and the SDT term. The SDT can act as antidamping, adding energy to sustain precession or drive switching when current exceeds the critical value. SDT decomposes into two orthogonal components. The damping-like torque, proportional to M cross MP, pushes magnetization toward or away from the pinned layer direction. It directly drives switching. The field-like torque, proportional to M cross MP, acts like an effective magnetic field causing precession. In metallic systems, the damping-like component typically dominates. These simulations show magnetization dynamics for different SDT strengths. With no SDT, magnetization simply damps to equilibrium. As SDT increases, we first see sustained precession, then increasingly faster switching. Above a critical SDT strength, the magnetization completely reverses from plus Z to minus Z. The transition from damping to switching occurs at the critical current. The critical current density JC is the minimum current needed to switch magnetization. It depends on damping alpha, saturation magnetization MS, free layer thickness TF, polarization P, and the anisotropy field HK. Reducing JC is crucial for low-power memory. Strategies include using low-damping materials, optimizing anisotropy, increasing polarization, and making the free layer thinner. Four main approaches reduce critical current. First, use low-damping materials like Co-Phi-B, which has alpha around 0.01. Second, optimize perpendicular magnetic anisotropy to lower the energy barrier. Third, increase spin polarization using MgO tunnel barriers, which give polarization above 0.5. Fourth, make the free layer thinner since critical current scales linearly with thickness. Each approach has trade-offs with thermal stability. SDT switching time depends on the current overdrive ratio J over Jc near the critical current, switching is very slow and variable due to thermal fluctuations during the incubation period. With higher overdrive, switching becomes faster and more deterministic. At twice the critical current, switching times of about 1 nanosecond are typical. There's a trade-off between speed and power consumption. STT-MRAM uses a magnetic tunnel junction stack. From bottom to top, electrode, synthetic antiferromagnet structure, fixed reference layer of Co-Phi-B, MgO tunnel barrier about 1 nanometer thick, Co-Phi-B free layer 1 to 2 nanometers thick, and cap layer. The cell is two-terminal. The same current path is used for both reading via TMR and writing via STT. STT-MRAM operation is elegant. To write 0, electrons flow from the pinned layer into the free layer, driving the free layer to parallel alignment with low resistance. To write 1, electrons flow the other way and reflect off the pinned layer, driving anti-parallel alignment with high resistance. Remember that conventional current runs opposite to the electron flow in both cases. Reading uses a small sensing current to measure resistance without disturbing the state. The shared read-write path is both a simplification and a challenge. STT-MRAM design involves fundamental trade-offs. Thermal stability factor delta must exceed 60 for 10-year retention. However, increasing delta requires a larger MTJ diameter, and that raises the critical current and the write power. The two requirements pull in the same direction, which is what makes scaling hard. The challenge is maintaining sufficient delta while reducing size and current. At 50 nanometer diameter, typical designs achieve delta around 70, with critical current around 50 microamps. For high-speed operation, processional switching is preferred over direct switching. By applying short current pulses, magnetization follows a processional trajectory that can be faster than damping-dominated switching. The pulse width must be carefully optimized. Too short causes incomplete switching, too long wastes energy and causes heating. Optimal pulse widths achieve sub-nanosecond switching. Write error probability in STT-MRAM follows a thermal activation model. Error probability decreases exponentially with effective thermal stability, which depends on both delta and the overdrive ratio. To achieve bit error rates below 10 to the -6, high thermal stability around 60, and sufficient current overdrive around 1.5 are required. This places constraints on both device design and driving circuits. STT-MRAM faces 3 main challenges. First, the shared read-write path creates red disturb risk where sensing current might accidentally flip bits. Second, incubation time variability from thermal fluctuations affects timing margins. Third, repeated high current pulses degrade the tunnel barrier, limiting endurance. These challenges motivate SOT-MRAM, which separates read and write paths. This Python simulation solves the LLG equation with spin transfer torque. The code implements precession, damping, and STT terms using SciPy's ODANT solver. Running simulations for increasing STT strength shows the transition from damped oscillation to full magnetization switching. The switching time decreases as STT strength increases above the critical threshold. Let's summarize Chapter 2. Spin transfer torque originates from angular momentum conservation when spin-polarized current enters a magnet. The Slinksiewski model quantifies the torque's angular dependence. The LLG equation with STT describes switching dynamics. Critical current density sets the minimum switching current. STT-MRAM is commercially available but has challenges that SOT-MRAM addresses. In the next chapter, we'll learn about spin-orbit torque, which overcomes STT-MRAM's challenges. SOT uses in plane current through a heavy metal layer to generate perpendicular spin current via the spin Hall effect. This 3-terminal structure separates read and write paths, eliminating read disturb and enabling higher endurance and faster switching. Let's continue to Chapter 3.